So we are going to slowly introduce that concept in the next few lectures. So most of you took the midterm. What's the feeling like? How did you guys do? Like thumbs up? It's okay. Thumbs down? I see few thumbs up, few okays. Okay, we'll see. Honestly, I thought it would be, I was surprised that most of you like stayed back until the end. I thought most of you would be finishing it earlier. Maybe you're all like extra cautious with your answers, so we'll see. So we are going to use Gradescope for evaluating your exam. So we are waiting for the scans to be done. Once that is done, probably by the end of this week, you should hear back from us on that. Okay, project 1 is out. Please check out Canvas for all the details about the project. You should have also gotten an email about this. If not, you will get it like pretty soon. And once you go through the project, if you have any questions, like please let us know. Okay, so today we are going to talk about out-of-order processing, and the main motivation for out-of-order processing comes from,
Will we have a topic on prefetching, or we are done with that?
We'll come back to that later.
Oh,
okay. But the level of detail that we had on prefetching, like in the discussion in the lecture, that should be enough for the project. Okay. So the main motivation for building out-of-order processors comes from the observation that there is a lot of instruction level parallelism, and we can exploit that to get better performance, right? So what does instruction level parallelism even mean? So the pipelines that we have looked at, the in-order pipelines, so they're also known as scalar pipelines. And the main downside of these scalar pipelines is there is a limit on the number of instructions you can commit or you can retire in each cycle, right? So in each cycle you can only commit one instruction. Like that is what we have been doing. And the main issue is that if you have some instructions which take really long time, maybe because they missed in the cache, or you have a branch misprediction or something like that, then that ends up delaying a lot of instructions which are placed after these long latency instructions, even though the later instructions have no dependency on this particular instruction. Because we follow a single pipeline, if something stalls in the pipeline, everything that is behind in the pipeline has to stall, and that ends up enforcing all of these unnecessary stalls, which reduces your overall performance, right? So this is the pipeline that we have been looking at, and the amount of instruction parallelism that we can expect in this in-order pipeline is basically the number of pipeline stages that you have. Right. So if you have five-stage pipeline, you can expect 5 instructions to be in flight at any given point in time. If you have 10 stages, you can have 10 instructions, but that is it, right? And each operation on like effectively takes 1 extra cycle to graduate, right? So your IPC is 1, and that is what you would see, right? But this is not enough for performance, and what we would like to do is what is called a superscalar design. So the idea behind superscalar design are that we have parallel pipelines effectively, where we have multiple instructions which are being executed in the same pipeline stage, right? So you have for example, you could have 3 instructions being fetched, and then 3 instructions being decoded, and then 3 instructions being executed in the same cycle, rather than 1 instruction. So if you are processing n instructions in each of the stages that you have, and let's say the total number of stages that we have is the pipeline depth, which is d, then the total number of instructions we are processing at any given cycle is d times n, right? Compared to before, if your pipeline stages are d, we are only processing d instructions in a given cycle, right? And with this, you end up with a peak IPC of n, right? Every cycle you can, if everything goes well, and then you can find the instructions to do the work, then you can retire n instructions every cycle or commit n instructions every cycle. So your IPC is n. So that is what like we are trying to get to. We want to retire or commit more instructions in a given cycle, right? But what are the real problems? What you will see is that because of dependencies between instructions, right, you might always not have the necessary instructions to fill up all the slots you have in the system, right? Let's say you see a branch instruction in the fetch stage. you don't know what the outcome of the branch instruction is going to be. You can predict, but until the next cycle you don't know what is the outcome of the branch prediction. So in that cycle you cannot fetch 3 instructions, right? If the first instruction is a branch instruction, the other 2 slots are going to go waste because you don't know what instruction to fetch. And then in the next cycle, based on the prediction, you know which way to go, right? And if you have long latency instructions and there are dependent instructions on that later in your instruction stream, you cannot execute those instructions until the long latency operation is complete. Right. So because of that, the problem that we see is that you have all these slots for instructions to be executed, but you're not able to fill up the slots with valid instructions. Right. So that is a problem with these in-order superscalar designs. Right. Like we have all these slots, but it is still operating in the synchronized fashion, where if you have some dependencies which makes it not possible for some later instructions to be executed, then you have all these stalls which will get propagated. So this is not a real solution as well. And what we realize over when looking at programs is that given a window of instructions, there are instructions which are dependent on each other, and then there are a series of independent instructions. And the idea is that these independent instructions can be executed ahead of dependent instructions which are present above them. That way we always have instructions to fill up these extra slots, and that is what we are trying to do, right? And the measure of how many of these independent instructions you can execute in a given cycle is called the instruction level parallelism, or the ILP of the program, right? ILP is a property of the program and also the property of how much parallelism your hardware allows you to do, right? So the average ILP is the one way to calculate average ILP is the total number of instructions that are present in your program divided by the total number of cycles required to execute these instructions in an ideal piece of hardware, right? So on the left side you have a piece of code where we have 3 instructions, right? But they are all dependent on each other. We are producing R1 in the first instruction, which is used in the second instruction, and we produce R3 in the second instruction, which is used in the third instruction, right? So these instructions have to be executed one after the other. So you'll necessarily even in ideal conditions, you can only execute one instruction every cycle. So your ILP comes out to be 1. Right? Whereas in the second set of instructions, you will see that there are no dependencies between these 3 instructions, and if you have the hardware resources to execute all of these 3 instructions in parallel, it is possible to do so without affecting correctness, and therefore the ILP in the second set of instructions is 3. Right? And the bet we are making is that there is a lot of ILP in our programs, and if only we have the hardware resources to exploit this ILP, we are going to get better performance. Right? And why is this a reasonable bet to make? There is a long line of research which has looked at applications from various different domains, and these are the ILPs they tend to report. Like some domains, they have an ILP of like 1.5, so you can execute 1.5 instructions per cycle on average, right? But that is at the lower end, and if you look at the higher end, there are these extremely parallel programs where you can have up to 90 instructions that you can execute in parallel, as long as you have the hardware resources to do that, right? So over all these workloads, we can see that clearly there are opportunities to execute multiple instructions per cycle, and then we want to build hardware that will allow us to do so, right? So once again, to stress the importance of why we need out-of-order processors, let's take a look at the problem with in-order processors, right? So we have a pipeline, and let's say we have separate functional units to do addition and multiplication, right? So addition and subtraction go to one kind of ALU, and multiplication is going to a special ALU, and it is reasonable to assume that the multiplication takes few more cycles to complete, right? So let's say if that is the pipeline that we are working with. If these are the 3 instructions that we have, right? So the add instruction is producing a result that goes into F2. The multiply instruction is using the value in F2. and it itself is writing to F2, and then you have a separate subtract instruction. Right? The subtract instruction has no dependencies on any of the two instructions above, but if you are using in-order pipeline, you will end up stalling the subtract instruction. Right? The multiply instruction has to stall for the add instruction. That makes sense because there is a true data dependency between those two instructions. Add is writing to F2, and then multiply is reading from F2. So if we want to execute the multiply instruction, we have to wait in the decode stage until the value of F2 is ready from the previous instruction, and once that is ready, we can go ahead and execute the multiply instruction. But the add instruction, the subtract instruction has no dependencies, but because the multiply instruction is stuck in decode stage, the subtract instruction is going to be stuck in the fetch stage until the multiply can go ahead, and only once the multiply goes ahead, we can go ahead and execute the subtract instruction. Right? So ideally, we would want to execute this subtract instruction even though the multiply instruction is stuck waiting on the add instruction. That way, by the time the multiply instruction is ready, our subtract instruction is also probably completed, and these three instructions will take fewer cycles to execute than in this in-order fashion. Right? And the way to do this is using a technique called dynamic scheduling. And the higher level idea of dynamic scheduling is that we should let instructions execute as soon as their operands are ready, and we shouldn't make them unnecessarily wait for instructions ahead of them. Right? So if my operands are ready, I can go ahead and execute. If my operands are not ready because some other instruction has to produce some result, then I'm going to wait for it. Right? So that makes some sense naturally. So the way we go about doing this is we are going to break up the pipeline into a front end and a back end. And in the front end, we are going to continue to fetch instructions and then decode them to figure out like what is the work that needs to be done for a given instruction and what are the inputs and so on. Once we have decoded these instructions, we are going to put these instructions into a structure called the instruction buffer. Right? So there are many different names for this structure, but we are going to use instruction buffer in this class. So we are going to put these instructions in the instruction buffer. That's where it's going to reside. And once we can determine if the input operands for an instruction in the instruction buffer are ready, then we are going to issue it to the back end of the pipeline where it is going to be executed and written back and other things. Right? So instructions are fetched and decoded in order, and then they are placed into the instruction buffer in order. And once an instruction has been placed in the instruction buffer, if its operands are ready, we are going to issue it and then execute the instruction. Right? And then we are going to do the write back and stuff. When we are doing all of this, we have to keep in mind that there might be true data dependencies between instructions, and we have to enforce these dependencies. Right? And there might be some structural or pipeline dependencies that might arise when we use this kind of a mechanism. Like this, let's say we are fetching some instructions and then we are putting them in the instruction buffer, and these instructions happen to be long latency instructions, right? So they take a while to execute, and because they are taking a long time to execute, we are fetching instructions and putting them in the buffer, but the buffer is not being drained as quickly as we are bringing in these new instructions. So your buffer might get full, and if your buffer gets full, then you have to stall your fetch stage, right? So we are not completely eliminating all of the unnecessary stalls that the program might incur, but we are trying to remove them as much as possible, right? And one of the key techniques that we are going to see that is going to help us with this is what is called register renaming. And the idea behind register renaming is that we are going to remove unnecessary dependencies between instructions that might otherwise exist. And what are these unnecessary dependencies? These are the write after read, war, or write after write dependencies. So if you think about it, yeah.
So for registering, why can't the compiler just do this for us? Why do we have to rely on hardware to rename, to remove these types of dependencies?
So the compiler only has, so if you have 32 registers, then your compiler can only use 32 registers. Right? That's what the ISA promises. And the idea is that you can, how do I put it? So based on the ISA specification, your compiler is limited, and because the hardware that we implement only has to give the illusion of the ISA being executed, right? We don't have to actually implement the same number of registers. So that is why this is a technique that works better in hardware than in software, like in the compiler. Yeah.
So couldn't this also be a case then to increase the number of registers that, I mean, if you already have the amount of registers allocated for the CPU to do processing on, couldn't that be a case for just extending the ISA to allow for more registers?
So when you extend the ISA, that involves a lot more things, right? So not all computers you are going to build have the ability to have those many registers, right? You write a program for x86, it should work on a small microcontroller, but it should also work in a server which is sitting in a data center, right? So the number of registers you can have in a small power-hungry microcontroller is going to be much smaller than in a data center, right? So that limits the number of registers that you can require as part of the ISA. Right. But in general, the more the number of registers, the better, and you won't run into these issues. But we cannot have as many registers as we would like in the ISA. In the hardware, we can have more than what we have in the ISA, but even in the hardware, we cannot have as many as we'd like. Yeah.
So then if you were creating a completely brand new ISA and you didn't care about compatibility issues with prior versions, this would be then a good case to just extend your register count to the front end.
Yeah. So if you have the hardware resources to have like a lot of registers, then sure, go ahead. Then you won't run into all of these dependencies. But yeah, anyway, so register renaming is a technique that you're going to see in more detail later. That is going to help us overcome these dependencies. But I'll give you a quick preview of how register renaming works, right? So let's say the architecture specification, the ISA, specifies that there are 3 registers that are necessary in the hardware, right? R1, R2, and R3, right? But what the hardware developer does is internally in the processor, we are going to have the space required for 7 registers, right? So we are going to have P1 to P7, right? And then we are going to have a mapping table that is going to map these architectural registers R1, R2, R3 to underlying physical registers P1 to P7, right? So initially when we start out with R1, R2, R3 are mapped to P1, P2, P3, and we have a free list of registers which contains P4 to P7. Right? As we execute instructions, these instructions are going to write to these architectural registers, and every time we find an instruction which writes to an architectural register, we are going to remap the architectural register to point to a different physical register, right? So consider this sequence of events, right? So if we have these 4 instructions, the first instruction add is writing to R1, the subtract instruction is writing to R3, multiply is writing to R3, and division is writing to R1, say, right? So we have the red arrows point to raw dependencies or true data dependencies. One instruction is producing a value, the second instruction is reading the value, right? So those are these red arrows. These we cannot do anything about because they are built into the program itself, right? But we have some, if you look at war or write after read dependencies, you will see that the division is writing to R1 and this subtract instruction is reading from R1. This means that the division instruction cannot write to R1 before the subtract instruction has actually read the value from R1, right? So we have to preserve the value in R1 until subtract instruction has read the value, and only then the division can write the value. Right? So this dependency only exists because both of these are writing to R1. If we can modify the division instruction such that it can write to a different location, say R5 or R6 if we had the ability, right? And then we won't have this dependency anymore. And if we have any true data dependencies on the division instruction later, we can tell all of them to get the value from R5 or R6 that we are going to write to. Right. So just because we share this register here between these 2 instructions, we have this unnecessary dependency, and similarly we have a write after write dependency that is also unnecessary. If we do register renaming, we can get rid of these two unnecessary dependencies. So after the add instruction, what we are going to do is that we are going to say that R1 now maps to P4. So we are going to rename the instruction to say add P2, P3. So these are the input registers we are getting from P2 and P3, and then we are writing the value to P4. Right? So every time we are writing to a destination register, we map it to a new location, right, as much as we can. So now once we say that R1 is now going to map to P4, we are going to update the mapping table to say that R1 now maps to P4, and R2 and R3 are still mapping to P2 and P3. Right? So now when we look at the second instruction, subtract, R2 maps to P2, so we are going to use P2 to get the value. R1 maps to P4, so we are going to read P4 to get the value. And then the destination register we are going to write to a new location, so that's going to be P5. But the architectural register, the architectural destination register was supposed to be R3. Right? So we are going to update the mapping table to say that R3 now maps to P5. Right? So that if there is any subsequent instruction which is trying to read R3, it is now going to go to P5 and get the value from there. Yeah.
Why originally the number of names are not equal to the number of actual locations?
Sorry?
Why the number of names are not equal to the number of locations?
So if you had R1 to R7, like if you only had P1 to P3 here, right? So then this renaming technique won't work.
Well, yeah, the renaming technique is working because the number of names is not equal to the number of locations. I'm asking why.
No, that's not true.
Oh, okay.
So if the number of registers or the number of names that you have is equal to the number of locations, right? So then you cannot do any renaming.
Right.
That means you have to reuse your architectural registers more often, and then you will end up with these dependencies because you have to reuse registers. There are no extra registers, right? But what we are saying is that if you have, or if we build in these extra registers in the hardware, we don't have to expose them to the software, we'll just do it at the hardware level. Then we can do this mapping, renaming business to get rid of these unnecessary dependencies. Right? Yeah.
I'm not sure if I quite understand how this works, but are we putting values into the register and then moving them from there to locations?
So when you write your program, like you say something like add R1, R2, and then put the value into R3, right? So this is how a compiler inserts an instruction, right? So one way to do this is have specific locations in your hardware and then say that R1 will always be written to this, and R2 will always be written to this location, and R3 will always be written to this location. So this is a valid design, but the problem with this is if you have only one location at which R1's value can be stored, then if you want to reuse R1, then you necessarily have to wait until all of the dependencies on this value have been resolved before you can write the new value of R1, right? But if you do that, then you end up with these write after write and write after read dependencies. What we are saying is that instead of having this kind of an architecture, let's move to a system where we have more physical registers available than architectural registers. And now your R1 can map to different locations at different points in time. And once you do this, you can remove these unnecessary dependencies.
And how would you know that R1 is pointing to a certain location like that?
So you will have a separate table called the mapping table, which maintains what is the current mapping between the architectural and the physical register file, right? So initially when we start out with, we say that R1 maps to P1, R2 maps to P2, and R3 maps to P3. But once we overwrite R1, or we want to overwrite R1, we are going to write the new value into this new location called P4. That way, if somebody wants the old value of R1, they can still get it from P1. But the new value is going to be written to P4. and anybody who wants the new value is going to read from P4. Yeah.
How is it encoded? The old value or the new value?
Sorry?
How is encoded? Old value is in P1, new value is in P4.
So when you do register renaming, what you will see is that you only ever need to maintain the new latest information, at least initially. And then we are going to get into cases where you have to maintain the old value a little bit later, right? So there are special structures where you maintain this information, but for the purposes of this discussion, you only need to maintain the new value.
So at any given point T in the execution, so a name can point to multiple locations.
No. So there is only one location.
Okay. So in the initial cycle, it was represented P1, P2, P3. Then it changed to P4, P2, P3.
Yes. So you only maintain at this point what is the mapping, or which physical register are you mapped to at this point in time. So that subsequent instructions can use the latest mapping to get the value out.
So then what's the point of having multiple locations? Because at any point...
Because you are not overwriting the old value in the old location. So if somebody is using that location already, they can continue to use that value and they don't have to worry about you coming and clobbering their value, right? So that is the issue here, right? So if we don't do register renaming, division is going to try to write to R1, right? And let's say subtract has still not read the value R1. Then in this design, if the division instruction goes ahead, it is going to clobber the value that the subtract instruction is going to read, and you end up with the subtract instruction getting a wrong value. So all of this problem arises because we are trying to execute instructions out of order, right? But now in this renamed design, if you look at division, it's going to write to P7, but subtract is still trying to read from P4. So this instruction can go ahead and execute and finish even while the subtract instruction is not yet completed, right? Any other? Yeah.
So for the renamed instructions, there's still read after write.
Sorry, the renamed instructions?
The renamed ones, there's still read after write.
Yes.
Can I see, is it possible if there were more locations, you could map like the P4 in the subtract to even another location and then get rid of the read after writes?
No. Actually, so that's a good question, in the sense that register renaming, how much ever you do it, you will never get rid of read after write dependencies, and that is not a bug, that is the feature, right? You should not get rid of read after write dependencies, because read after write dependencies are true data dependencies. You want one instruction to get a value from an earlier instruction, right? So here the add instruction is writing to R1 and the subtract instruction is reading from R1, right? So the add instruction is producing a value, the subtract instruction is consuming the value, right? So you want to maintain that dependency even when you rename the instruction. When it comes to these other dependencies, there is no true data that is being flowing from one instruction to another instruction. They just happen to depend on each other because they are reusing the same register. Yeah.
So does the free list get repopulated again? So
yes.
Okay.
So once we are done with this instruction, right? So then we don't. So if you look at this instruction, R1 was originally pointing to P1. And now we are saying that after this instruction is done, R1 is going to point to P4. Once this instruction is completed and all prior instructions have been completed, then we know that nobody is going to need P1 anymore, right? So at that point, you put P1 back into the free list, right? So that is the case where you remember the old value. But for this discussion, like, we don't have to worry about it. Yeah.
So far we've seen like too many buffers and registers. All of these are saved and flushed on context switches.
You don't have to save all of them.
But flushing them and refilling them.
So what you will see is that there is a subset of all the things that we have seen that are saved and flushed, right? So the main idea is that there is some architectural state that you have to maintain, in order for the context switch to work, like the value in the registers and stuff like that. So if you need the values in the registers, then you have to flush the mapping table also, because you need to know which is the value you need to copy and stuff like that, right? So there are some pieces of state that you have to maintain, but some state, like values in some, like the instruction buffers and things like that, those can be flushed. You don't have to worry about that. Right. Okay. So what is dynamic scheduling or out of order execution? So the idea is that we are going to dynamically figure out what are the instructions whose operands are ready, and we are going to go ahead and execute these instructions even ahead of earlier instructions which might be stopped, right? So that is where the term out of order comes from. So the main idea is that we fetch as many instructions as possible, right? And if we find a branch instruction, we are going to predict the outcome of the branch and go ahead and execute, go ahead and fetch more instructions. And once we get all of these instructions, we are going to put them in this structure called the instruction buffer, right? So if we realize that we misspeculated at some point, then we have to flush out all the instructions we fetched along the wrong path. So we are going to get into that later. But the general idea is that you predict, and most of the times your prediction is going to be right. So you're going to fetch these instructions and put them in the buffer. And then we are going to rename these instructions so that you don't have any of these write after write or write after read instructions, dependencies. But we are going to see why these are very, very important, and then, or why renaming is very important in today's lecture. And then as soon as the input operands for a particular instruction are ready, we are going to go ahead and try to execute these instructions. And once we are done executing instructions, we are going to commit instructions in order, right? So we cannot commit instructions in the order in which we execute them. We still have to commit instructions in order, right? So the reason for that is because we don't want to astonish the programmers, right? The programmer expects that if you have an add instruction and a subtract instruction or whatever, that the processor is executing these instructions in this order. If the processor executes these instructions in any order it chooses, then if there is a bug or if there is a crash, the programmer has no way of knowing if the correct thing was done or the wrong thing was done or what to expect, right? So we still have to provide the illusion to the programmer that things are being executed in the correct order. But what we are going to do underneath the hood without the programmer knowing is we are going to execute these instructions out of order while respecting all dependencies, so that we can guarantee functional correctness. At the same time, we can get better performance, right? So all of this out of order execution is transparent to the programmer. They have no idea this is happening. Yeah.
So we weren't using any of these. Like
Sorry?
We weren't using any dynamic scheduling or renaming in the previous designs.
No. No. Yeah.
What does commit exactly mean?
Commit exactly means the point at which you say that the instruction is done.
Like if it is a load store, if it is stored, then it's failing to the memory.
No. It is the point after you send it to the memory. Actually, stores are like particularly complicated, so we'll get into that later. But for add instructions, you can say that you commit once you write back the value to the register. Or for a load, you can say that you can commit after you're done with writing the value that you loaded into the register, right? And what specifically or what exactly commit means will become more clear once we look at out of order processors.
I was wondering, like, how long do we check for dependencies? Because given a huge program and the number of registers we have, we will eventually run out of registers, and we'll have like a dependency between the first instruction and let's say the 1000th instruction. So how long do we check for?
So usually it's in the hundreds. Like for the latest out of order processors, the window in which we do all of this out of order execution is in the hundreds. Okay, so this is more of the same. We are going to reduce all of these stalls, and then we are going to execute as many instructions as possible in a parallel fashion so that you can exploit ILP and then get much better performance. But the challenge is that we still have to make sure that the execution appears to be sequential or in a serial order to the programmer, and that makes things a little more complicated. And then we are going to see why that is the case in the next few lectures. right? Okay, so what are we going to do next? So we are going to first talk about a simple out of order scheduling, which was first introduced, called scoreboarding. And this technique doesn't have register renaming, right? So this is one way to like ease into how dynamic scheduling works. And the problem with this approach is that it doesn't have register renaming, so the performance you get is not as good as you can potentially get. And then we are going to talk about Tomasulo's algorithm, right? And that algorithm introduces the whole concept of register renaming, and you'll see how that makes a lot of difference in performance. And then we are going to talk about the challenges that arise from trying to preserve this illusion of in-order execution when we are doing out-of-order processors, and what are the challenges and how are these solved. And we are going to look at that by looking at this specific architecture called the MIPS R10K. So this is a commercial processor that was developed, right? And then we are going to talk about the issues that arise when we are dealing with memory dependencies and so on. So there is going to be like a series of lectures where we are going to slowly but surely we are going to build towards more and more like complicated out-of-order processor mechanisms, and towards the end you will come up with some design which is, I wouldn't say close to real architectures that we have today, but it is a good representation of the architectures that we have today, right? Okay, let's do this. So this is the in-order pipeline that we are familiar with, right? So we have these stages, and we are going to use one cycle for each pipeline stage, the familiar thing that you're aware of. But then one thing that we are going to make a note of is that we are going to have separate pipeline stages for integer instructions and floating point instructions. That is the assumption that we are making. And floating point operations take 3 cycles to complete, whereas your integer operations take 1 cycle to complete, right? This is just for the example to make sense. Like you will see that it makes more sense once we go through the example, right? So, and instead of having a pipeline diagram, we are going to have these tables that tell us what are the different stages in which different instructions are and how long are they going to take, right? So we have these sequence of instructions, and all of the instructions which end in F are floating point instructions, and all the instructions which end in I are your integer instructions, right? So the first load instruction, it was dispatched or it was decoded in cycle C1, right? And then it was executed in cycle C2, and it was returned back in cycle C3. So that is the way to read this. And then the multiply instruction, this one here, was decoded in C3. It began execution in C4, but we said that floating point operations take 3 cycles. So that's why we have the plus to denote that. And then finally, it is going to be written back in cycle C7. Right, so that is the way we are going to read these diagrams, and they are useful in understanding when and where these different instructions are being executed in the pipeline, right? So we have the in-order pipeline, and the main problem with these in-order pipeline is that younger instructions cannot pass or overtake older instructions when they are being executed. And that's why we have all these unnecessary stalls. And then we want to implement this passing mechanism in hardware so that we can execute instructions out of order and then get better performance, right? And the way to do that, yeah.
Is it still like one issue, or is it multiple issues?
At this point, you can think of it as one issue, like it doesn't make a difference. Yeah, but we are going to fetch one instruction every cycle, right? So what we are going to do is, the main trick is to have this separate structure called the instruction buffer, which divides your pipeline into a front end and a back end. So the front end fetches instructions and puts them into the buffer, and the back end now tries to figure out which are the instructions which have their values ready and then executes them out of order, right? So we accumulate the decoded instructions into the buffer in order, but we execute them out of order, right? So we are going to see how that is possible. Right. So the main thing to note is that the decode stage is now broken into 2 different steps. There is the dispatch stage and there is the issue stage. right? So what the dispatch stage does is, it's the first part of decode, and once we get an instruction from the fetch stage, we are going to allocate a slot for it in the instruction buffer, and then we are going to decode this instruction, right? So the main thing to note here is that we are introducing a new kind of structural dependency or structural hazard, where we say that we're going to put these instructions in the buffer. So if the buffer is full, then later or younger instructions will have to necessarily stall, right? But as long as the buffer is not full, we can continue to decode instructions and put them into this instruction buffer, right? And then the second part of decode is called issue. And the main idea behind issue is that we are going to look at instructions whose input operands or input registers are ready for us, and then we are going to issue those instructions to be executed, right? So here, younger instructions don't really have to wait for older instructions to be completed, because as soon as their input operands are ready, an instruction will be executed, will be issued to be executed. So that is the second stage issue, right? And then you can have these many different pipeline or functional units, as many as you'd like, to execute these instructions in parallel, right? So you can have one ALU which does all arithmetic operations for integers. You can have a different ALU to do multiply operations, for example, separate for division, and you can have a simpler ALU as well, right? So you can have multiple functional units, and the idea behind having these multiple functional units is that we can, if you have these multiple different instructions, you can issue them in a parallel fashion. Let's say you have an add instruction followed by a multiply instruction. We can let the add instruction go ahead first, and then we can let the multiply instruction go ahead and execute in the multiply functional unit, and both of these are happening parallelly, right? So that way you get better performance. So we have these multiple functional units, and then we are trying to utilize them as best as we can, right? So that is the main motivation behind dynamic scheduling, right? So we're going to look at two different scheduling mechanisms. So one is called scoreboard scheduling or scoreboarding. That is what we're going to cover in today's class. And what you're going to see is that scoreboarding doesn't have register renaming. That limits how much dynamic scheduling we can do. And then in the next class, we are going to look at Tomasulo, which introduces register renaming, and then it shows you how much effect it has on overall performance, right? And there is a big simplification that we are doing in this lecture and in the next lecture, where we are not worrying about memory scheduling, where you schedule memory operations. We are going to be focusing only on the pipeline for these two lectures, and then in the next few lectures, we are going to introduce memory scheduling and the complications that brings. Right. Okay, so how does scoreboarding? Yeah.
By memory scheduling, you mean the commit order that you have to define?
Memory scheduling is the order in which you issue memory operations.
So when does commitment happen? The ordering for committing the final instruction.
So we are going to get into all of that later. So all of that happens a little bit later. So it's useful to go in this series of lectures. Okay. Okay. So what we are going to do with scoreboarding is we are going to have this structure called the scoreboard, which is a centralized control scheme which tracks the status of individual instructions, and then that helps us determine what is the order in which we can schedule these instructions, right? So there is a special table called the functional unit status table, or FUST, that maintains the status of different instructions and also different functional units, so that we know what can be done. Right. So the first implementation was in a commercial processor called the CDC 6600 from 1964. And one thing you can note, one thing you can all remember, you should remember, is that most of the techniques that we are going to talk about in this class, entire semester, IBM has come up with them in the 1960s and 70s. So these techniques have been around for a while, and you can blame IBM if you find this course hard, right? Okay, so we're going to use a simple scoreboard in this lecture. It has 5 different functional units. There is an ALU, there is a special functional unit that handles load operations, there is a special functional unit that handles store operations, and then we have 2 floating point functional units, each of which takes 3 cycles. The rest we assume all finish in 1 cycle, including the memory operations. Right? So what are the data structures that we are going to use in this scoreboarding scheduling technique? I'm just going to give you a quick overview. You don't have to remember all of these now. Once we go over the examples, like these things will become more clear to you when you revise, right? So there is a functional unit status table that maintains the status of each of the 5 functional units that we discussed in the previous slide. The kind of information it maintains is what is the functional unit, is it busy or is it free now? If it is busy, then what is the current instruction that is running on it, what are the input registers, what are the output registers for those instructions, and so on. Right? And then for each of the input registers, we are going to have a value called a tag, and the tag essentially specifies where this input register value has to be gotten from. It could be present in the register file, then we just get it from the register file, or it could be that some other instruction is producing this value. Then we have to maintain this information that we are going to get the value from somebody else, so that we can wait until that operation is complete and then we can get the value. So in order to do that, we have this special tag field, and then that will make sense once we go over the example. And then we also have a tag for the destination register. So we have to maintain this tag so that if there are any dependent instructions later, we can go ahead and give them the value at a later point, right? So it seems a little fuzzy now, but trust me, like all of this will make sense in a few slides. And then we have a special table called the register status table, which maintains the tag for each of the individual register. So who is responsible for providing the latest value for that particular register is maintained in that status table. And these tag values, the way to read them are they are either 0 or non-zero. If they are 0, then the value is ready and is present in the register file, and that is where we get the value from. If it is non-zero, then the tag value tells us exactly who is going to supply the value. Right? So we wait for that person or that entity to provide the value. And then finally, we have an instruction status table that maintains if an instruction has been issued, has it been executed, and so on. And this is also useful in figuring out these dependencies. Right? Okay, so this is a high-level overview of the pipeline or the structures that we are going to use for dynamic scheduling. So we have an instruction table that maintains the status of these different instructions. We have a register status that tells us for each of the registers that we have in the processor, what is the corresponding tag. And the tag value tells us who is going to provide the latest value of that particular register, right? And then we have a register file where we store the values, these individual registers. And then okay, sorry, my animations are screwed up. So we have a functional unit status table that is going to maintain the information about what are the different functional units, are they busy, are they free, and if they are busy, what is the instruction that is currently occupying them, what are the input operands, and what are the corresponding tags, and so on. Right? So let us go through this and then you will see. Okay, so this is more for your reference, but we'll come back. This should be clear once we go through the example, right? So what we are going to do is when we are trying to schedule instructions to a particular functional unit, we are going to check for any write after write or structural dependencies. Right? So if some instruction, so if we are trying to schedule a multiply instruction, and if we see that some other multiply instruction is already using up the multiply functional unit, then the functional unit's status table will tell us that, oh, this functional unit that you're trying to use is already being used by somebody else, so then we stop. Right? So if you are trying to write to a certain register, the destination register of a particular instruction, and the register status table will tell us that, oh, somebody else is already trying to write to this instruction, this register, and they are currently being executed, then we have to wait until that instruction is done, and then only we can go ahead and issue our cells, right? And then once we get the functional unit and we are ready to go ahead and issue this instruction, then we copy the register status for the input registers into the status table here, so that we know where to get the values from, right? And then finally we are going to set the register status for the output register, right? Okay, so what I'm noticing is a lot of blank faces, so let me go to the example and then we can work our way backwards from there, right? Okay, so this is the series of instructions that we are trying to execute, right? So we have the load instruction first, right? It is getting a memory address from R1, adding X to that, and then doing the load operation, and then the output is written to F2. So the register on the far right is the destination register for each of these instructions, right? Store instructions, they don't have any destination registers, and we have a destination register status table that maintains the status for each of these instructions, right? And then we have a functional unit status table that maintains the status of each of the functional units that we have in our system. So we have an ALU, we have a load functional unit, we have a separate functional unit for store, and then we have two floating point functional units, FP1 and FP2. Okay, so let us see how we schedule these instructions, right? So first we have the load instruction. Because it's the first instruction, there are no dependencies, it is going to be dispatched in cycle C1, right? So that is the information we maintain here, C1, right? And we know that the load instruction is going to write to the register F1, right? So if anybody wants the latest value of F1, they have to wait until this load instruction is done with executing, and only then the latest value of F1 has been saved, right? So to register that information in the register status table, we say that F1 is going to be tagged with the load instruction or the load functional unit, and until the load functional unit is done with the execution of the current instruction, the F1 value is not ready for anybody else to use, right? And in the functional status table here, we say that the load functional unit is now busy with the LDF instruction, and the destination register for this is F1, right? And we only have one input register, which is R1, and if we look at the register status for R1, it is blank. That tells us that nobody is currently trying to produce the value of R1. So we can go ahead and use the value of R1 that is present in the register file, right? So maintain that information, and if you look at the two statuses here, because we don't have any R1 that we are waiting for, this is blank, and because the value of this R1 register is present in the register file because nobody else is trying to produce the value, this is also left blank, and then we are done. Right? So what does this functional unit status table tell us about the load instruction? That the input operand is R1, the output register is F1, and we have no dependencies on any previous instructions, so that we can go ahead and issue this instruction to be executed in the next cycle, right? Okay, so let's move to the next cycle, cycle 2, and let's see what happens. So in cycle 2, if we look at the input operands for the load instruction, we don't have any dependencies, we are not waiting for anybody to finish, so we can go ahead and issue this instruction in C2. At the same time, we look at this next instruction, and then we can dispatch this instruction into the functional unit status table. Right? So this is a multiply instruction, and it's a function. It is a floating point instruction. So we try to issue it, or we try to dispatch it into this slot here. So in this slot, we are going to say that this floating point unit is now busy with the multiply instruction, and the output register is F2, like you can see here, and the input registers are F0 and F1. And for F0, we look up the register status table. That tells us, because this is blank, that tells us that no previous instruction is going to try to produce the value of F0. So the value of F0 is the value that is present in the register file, and we can use that. So we set the tag to be blank or null. But if you look at F1, the second input operand, and we look at the register status table, that tells us that F1 is, the value of F1 is going to be provided by the load functional unit, right? So we tag the F1 register with the load functional unit such that later when the load instruction is executed and it produces the value, it is responsible for making sure that this instruction gets the right value. So we maintain that dependency information in the functional unit status table, right? So by looking at the functional unit status table, now we can say that, oh, this instruction, it can only be issued when the input operand F1 is made available by the load functional unit here. Does it make sense? Any questions? Yeah.
Is the register status table only for destination registers?
No. These, so, oh sorry, the register status table.
Yeah.
So this maintains who is producing the latest value for a particular register, and by definition that has to be the destination register for some instruction, because, right? Okay, so let's move to the next cycle. So in the next cycle we have, so in cycle 2, if you notice here, we have issued the first load instruction because it has no dependencies, right? So this can go ahead and execute. So we are going to issue that in cycle 2, and in cycle 2 we also dispatched the multiply instruction. So now in cycle 3, the issued instruction is go ahead, like it will go ahead and issue, it will go ahead and execute. At the same time, if we look at the multiply instruction, its input operand is waiting on the load instruction to produce the value. So that will only happen after the execute stage. So we cannot issue this instruction. But we can go ahead and dispatch a later instruction, right? So we are going to get the store instruction, and we look at the store unit, and it was, if we go back to the previous cycle, it is not busy. So we can have the next instruction take up this slot. And then we maintain information that the store unit is waiting on this, or it's going to execute this store instruction. The input operands are F2 and R1. Right. Again, for these two input operands, we look up the register status table, and we see that for F2, the value of F2 will be produced by the instruction which is present in the FP1 functional unit. So we are going to make a note of that here in the tag field. And for R1, it is blank. So we can get the value from the register file, so we don't make any note of that, like it's also left blank, right? So we have allocated the store instruction in your functional unit status table. Right. Okay, so now some interesting things are starting to happen. So the load instruction completes in C3, or it is executed in C3. So now we can write back the value in C4. Once we write back the value for a load instruction, we can consider it to be done. Right? So we are writing back the value in C4. Once we write back the value, the latest value which was loaded is now going to be present in the register file. It is not going to be produced by any other additional instruction, right? So we are going to clear the load or the tag for F1 now, because any future instruction which tries to read the value of F1 can simply go to the register file and get the value. It does not have to wait for any functional unit to produce the value, right? So if you look at the load here, we have an underscore here. That means that we are clearing the value of load in the tag, right? And if you look at things in the, at the same time, if you look at the multiply instruction, now we have the value of the register. Where is multiply? It's here. Yeah. So F1 is ready because the load operation is completed. So now we can go ahead and issue the multiply instruction because the input operand is ready, and we can use that value to execute the multiply instruction. So in C4, the multiply instruction is issued, right? And then finally, if we look at the add instruction here, the fourth instruction, we look at the ALU unit, that is empty. So we can place the add instruction in the functional unit status table, and we have one input operand R1 and we had one destination register R1. So we maintain that information, and if we look at the input tags, R1 was free, like nobody else was using or producing R1, so these are left blank. But now this add instruction is going to write to register R1. So anybody else who wants this value will have to wait until the ALU unit is done with its execution to get the latest value of R1. So we note that piece of information here in the register status table, right? Any questions on this? Okay, go ahead.
So it seems that the this is like redundant because the presence of the instruction there is indicating that okay, that line is busy, whatever.
Yeah, but in hardware you need a bit to say are you occupied or not occupied, right? So that is what this yes no is like trying to signify. Yeah.
So the value F1 is getting written in cycle 4.
Mm-hmm.
And the same thing is cycle 4, but the same thing is fetched back also in C4. So
Fetched back. We are just issuing the instruction.
So that doesn't need the...
So it needs the value, but if you remember we had the half cycle thing, so we are doing the same thing here. So you can write and read from the same register in the same cycle because you use different halves of the cycle. Yeah.
So you say like all floating points are 3 cycles, but load is floating point, but it's 1 cycle.
Okay, so good question. That is a bug in the slide. So when I say floating point, I mean these like multiply instructions mainly. The load and store instructions, they take 1 cycle only, and they have their own separate units. Okay. Any other questions on how we are tracking dependencies between different instructions? So now I'm going to ask one of you to interpret what like this line means. Any takers? Okay, actually let me ask something else. Can somebody tell me what happens in cycle 5? Okay, so this is the output. Can somebody like decipher this for me? Okay, let's break this down further. So what is happening to the multiply instruction in cycle 5? Go ahead.
It's going to execute for like 3 cycles.
It can, yeah, it will now execute for 3 cycles. And why is it starting execution in this cycle? Because we issued it in the last cycle when its input operands were ready, right? Okay, so what is happening to the add instruction in cycle 5? Anybody? Somebody in this area? Generally, more blank faces. Yeah, go ahead.
It's being fetched.
The add instruction is being fetched?
No, it's being issued.
Okay, and why are we okay with issuing this instruction in this cycle?
Because the previous dependency is now available. So we needed the value of R1 and it's now available, so you could use it.
So you just have to look at the functional unit status table, right? So for the add instruction, if you look at the tags of the input operands, you will see that we don't have any tags. That means that we are not waiting on any prior instructions to produce the value of R1. It is already available to us in the register file. So we can go ahead and issue this instruction in this cycle, right? Any questions? Okay, anybody who can tell me what is happening with the load instruction, the second load instruction in cycle 5? Yeah?
F1 is being specified as a destination.
Mm-hmm.
R1 is a source,
Mm-hmm.
and there's a dependency with the ALU
Mm-hmm.
because of the add instruction.
Yep. And we allocate an entry for the load instruction in the functional unit status table, right? At the same time, we make a note here that F1, the latest value of F1 is now being produced by the load functional unit again, right? So we make a note of that in the register status table also, right? Make sense? Okay. So now So we are in cycle C6 or cycle 6. The multiply instruction is going to continue with the multiplication operation because the multiply is going to take 3 cycles, right? So that is denoted by the C5 plus over there. And then we have the store instruction right after that here. We would like to issue this instruction, right, ideally. But if we look at the conditions for the store instruction, what you're going to see is that it is waiting on this register F2, and the F2 value is going to be produced by the instruction in functional floating point unit 1, FP1. So until the multiply instruction is completed, the store instruction is not going to get its F2 value, and so we have to wait until that instruction is done for this instruction to be executed, right? So we have to wait until the multiply is done before we can issue the store instruction. But that is not stopping us from executing the later instructions, right? So we've already issued the add instruction. So now we can go ahead and go into the execute stage where we are computing the value of the add instruction. And if we look at the load instruction here, the load instruction is waiting on the ALU to complete the add operation. So we cannot issue this instruction in this cycle. We have to wait until the next cycle. And then we have the multiply functional unit, or the multiply instruction. It is also trying to write to F2. And we cannot even decode this instruction because of 2 reasons. So one is that if we cannot issue this for one reason, and the main reason is that there is a write after write hazard. If we look at the multiply instruction here, it is trying to write to register F2, and if we look at the register status for F2, we know that there is an instruction in floating point unit 1 that is already trying to write to F2, right? And we have to wait until that operation is complete before we can go ahead and issue this instruction or even decode this instruction, right? Yeah.
In order, we say like we wait until the decode stage. I mean the second stage, right? So isn't our dispatch similar to fetch? Mm-hmm. Then shouldn't we wait until the issue stage?
You could, but if you decode this instruction or if you dispatch this instruction, you will have to change the register status. So now this FP1 would be changed to FP2, and you cannot do that until this is cleared, right? So you have to wait until that operation is complete. Okay, any questions? Yes?
Which unit is checking the dependencies? I thought the code was doing that in the in order scenario with the comparative.
Yeah.
So which unit should do?
It's the same, right? So the dispatch unit will look at your register status, and then that will tell you if there is a write after write dependency, and then it will not do the dispatch operation. Right? Okay, sorry. Okay, so that is cycle 6, and then we move to cycle 7. And if we look at cycle 7, what you'll see is that the multiply instruction is still being executed, right? It's going to take 3 cycles. So that is still being executed. There is nothing to do about that. And until the multiply instruction writes back the value, the store instruction cannot be issued. So we are continuing to wait for that with the store instruction. The add instruction, meanwhile, has completed its execution. And ideally, we would try to write back the value, right, in this cycle 7. But what you are going to see is that if we try to write back the value of R1 here, then the store instruction here has an input which uses the value of R1. So if we overwrite the value of R1, the store instruction is going to get the wrong value whenever it gets issued. So we have to stall the write operation or the write back operation of the add instruction until the store instruction here is done, right? So how do we identify that we have a potential write after read hazard and we have to stall the add instruction from doing the write back? We again look back at the functional unit status table, right? So if we look at the functional unit status table for R1 here, so what we are basically going to do is that we know that the add instruction is going to write to R1. So we are going to check for all the instructions in this table which are taking R1 as an input, right? So if we look at those instructions, we will find that there are two instructions. There is a load instruction and a store instruction, which are both taking the value of R1 as input. For the load instruction, the tag says that the ALU is going to produce the value that we are going to use for that instruction, and the add instruction is the instruction in the ALU. Right? So we know that the add, if I were the add instruction, I know that I'm going to produce the value that this instruction is going to use, the load instruction. So I'm not that worried about it. It's going to get the value from the ALU unit. But this store instruction, it thinks that there are no dependencies on the R1 and it can get the value from the register file. So that tells me that this instruction was scheduled before myself, the add instruction was scheduled. So this instruction is ahead of me and I cannot override the value of R1 because this is waiting to read the value from the register file. So a match in the input registers and a blank status in the tag field tells me that this instruction is actually going to read the value from R1, which I'm trying to overwrite. So now I have to stall myself until this instruction has been issued and executed. Right? Does that make sense? Okay. So this is a right after read dependency that we want to overcome. Right? Okay. So now in cycle 8, in the next cycle, the multiply instruction is done. So it is going to go ahead and write back the value, right? And then we are going to clear the FP1 tag here for the register F2, right? So if you look at the multiply instruction, it is going to write to register F2, and I'm doing the write back here, so I'm going to clear the value of FP1, the tag that was present. And the store instruction here can now go ahead and issue because its input value of F2 is being written back in the same cycle, so I can go ahead and issue this instruction. And the add instruction still cannot write back the value of R1 because this instruction is going to read the value in the execute stage, right? And then we have the multiply instruction here, which can now go ahead and be dispatched. We are going to use the second functional, floating point unit here, FP2, and we are going to note down the values like we did before, and we know that the value of F1 is dependent on the load instruction, so we are going to note that here, right? And for the store instruction, which is for the store instruction here, we maintain a tag of, we used to maintain a tag of FP1 because we were dependent on that. That is now cleared, so we can go ahead and issue that particular store instruction, right? And in the register status here for F2, we maintain a new tag of FP2 because we have the multiply unit which is now going to write to F2, and that is using the floating point 2 unit here. So we make a note of that here. Right? Any questions? Okay. So in the next cycle, what we are going to do is we are going to go ahead and execute the store instruction here, and because this store instruction has now read the value that it is going to use in cycle 9, we can go ahead and write back the value in this cycle. So you can write back the value of the add instruction. So the war dependency has been resolved now. And then we can go ahead and issue the load instruction, which was waiting on R1 to be written back. So since this has been written back in cycle 9, we can go ahead and issue that particular instruction in that cycle. And what is the next instruction? We have the store instruction, which is going to read the value of R1 and write it to, it's going to read F2 and R1. And what are we doing with the store instruction? Yes, with the store instruction, if we look at the functional unit status table, you'll see that the prior store instruction is still using the functional unit slot here. So your functional unit slot says that it's busy. So we cannot issue or we cannot dispatch another store instruction while one store instruction is still pending, Right? We can only have one instruction use the functional unit slot in a given cycle. Right? So because of that, we cannot dispatch the store instruction. Right? I guess we are done with time. So this is my last slide for today. And in the final 10th cycle, what you will see is that we have the store instruction that writes back the value. Why do we have a write back? Okay. Okay, anyway, so I don't want to take more of your time, so we'll continue from here in the next class.